All right. Good morning again. So today we are going to continue talking about modeling transformations, and then we will start viewing transformation if we have time. Remember, we talked about how we can represent transformations as matrix multiplications, and we have given some examples of composite transformation in which, for example, rotation of a point around an arbitrary or rotation of in this case, for example, rotation of this triangle around the pivot point in alpha degrees. Okay, so we have we worked out a solution on this, but actually I can start just this, and I can put these a little bit towards right. All right, so and our solution first was to solve this problem, to find the basic rotation by solving this trigonometric problem, geometric problem, in which we solve this part phi, this part theta, so rotation around origin theta degrees. And we have laid out this formula, which comes from the fact that this cos phi plus theta is cos and minus sin, and this sin. So the sine phi plus theta was this, and we figured out that okay, certain part of this was this formula was the original coordinate. R cosine alpha phi is the original x coordinate. So x coordinate times sine theta. If you multiply the x coordinate by sine theta, and if you multiply this time, so both of the sine phi, okay. So this was the y coordinate. If you multiply the y coordinate with cos theta, if you add them up, you're going to find your new y coordinate, and it's laid out here. So the rows of a transformation matrix tells us how much of the first coordinate we are going to get, how much of the second coordinate we are going to get, and we add up all these things. So this was the 2 by 2, but we actually went we immediately went into the idea of trying to do multiplicative transformation for all translation, rotation, and other linear transformations, which we worked on 3 by 3 matrices. Okay, and look at this. I mean, on the slide, the formula is just given as a laid out formula like this. It may be difficult to come up by just looking at this, but as we have talked about earlier, this is nothing but a composite transformation. Which is if you want to rotate a point around point P around the pivot point, what you need to do is you can first translate this pivot point to origin, move all of them so that this P is somewhere like this. Okay, so this becomes like XR, YR is going to be here, but since this becomes origin, this new P, it can be rotated easily around origin theta degrees. Then we move the point XR, YR back to its original location, which will help us find P prime. So with 3 transformation in a certain order. By the way, the order of these transformations is extremely important. Although matrix multiplication is associative, it's not commutative. All right. If you change the order of transformations, you get something else. You may end up with a completely different place where P prime is supposed to be. Okay, you're not going to find the correct P prime. So the order of multiplication is really important. This also tells something to us. It's really this part is really interesting, which is, for example, if you have a triangle in your OpenGL program or in ray tracing. I'm telling you this in terms of an OpenGL program because all these transformations we apply in OpenGL, they actually multiply a given modeling matrix. So let's just again jump ahead. So what we did was we had, for example, if you want to rotate this triangle's one vertex, okay, let's call this V1. So this is where V1 X, Y is, we represent these points as column vectors. Okay, it's in 4 dimensions in homogeneous coordinates. We have it like this. And why do we need this 4th dimension? Again, to be able to perform something like this. X prime is equal to ax plus bx. So ax plus by. I told it wrong, but I wrote it correctly. Then c, z, and d. Okay, if you want to have a linear combination, if you want your x prime to be a linear combination of the others and with an added constant term, the way to do that is to have them appear as these constants. If you have them appear as all 4 of them, okay, because as you can see, there are 4 coefficients here. With the added constant, we need a row with 4 values. Therefore, we can multiply this a row of 4 with only 4 values. If you a 4 by 4 matrix can be multiplied by a 4 by 1 column vector or 4 by 1 matrix, and then what you will do is you multiply these with these 1 by 1, and that becomes your whatever the result of this will be another 4 by 1 matrix, and that will be your x prime at the top. All right, so as you can see, d multiplied by 1 immediately says that we can, in order to add something with no xyz influence, if you want to add a constant directly to some value, you need to have these 4 by 4 matrices. Now, the thing that we do is, for example, if you want to rotate this triangle around its center of mass, for example, you want to rotate it so that it appears rotating around its center of mass like this. And if this was where the origin is, this is where the origin is, 0, 0, 0. And let this be the x-axis, y-axis, and this is the z-axis. So in a right-handed coordinate system, z is always going to be towards you if these are the x. So this one actually shows a right-handed coordinate system. In a left-handed coordinate system, the z could appear like this. Okay, that's also possible. So this is also a coordinate system. It's a valid coordinate system, but it's not right-handed. It's called a left-handed coordinate system. And some programs may be using these left-handed coordinate systems. Or, I mean, the way that I show these things, it may change in different modeling tools. For example, in some modeling tools, this may be z, okay? This may be x. And if that's x, where is y going to be? Y is going to be like this, right? This is also a right-handed coordinates. Is this, when I tell you, is this left-handed? Because I told you that when the arrow is towards the other direction, it's left-handed. But is this left-handed? No. In order to see that it's right-handed, all you need to do is rotate this like this. If you rotate it like this, x is going to be towards right, y is going to go up, and z is now pointing. It's the same thing, just rotate it. All right. Now, let's get back to the problem. If I wanted to rotate this triangle around its center of mass or around its central point, what I do is I first move the triangle's center to this origin, and with that, which means that I have to move this vertex as well along with it. I move the entire triangle. I change my frame of reference by doing this. When I do that, that's this translation. So first translate, and then do the rotation around origin, because that's the basic transformation. Some of these transformations, we call them basic transformations, like rotate around origin, rotate around x-axis, rotate around z-axis. Okay, so these are like basic transformations, and they may be readily available to you in terms as functions. So if you want to do something complicated, complex, you compose them into more complex transformations by calling them one after another, by sequentially, with a cascade of these transformations, you create yourself a more complex transformation. This is what we do. So whatever t was here, actually, we could, so it can be the inverse of t. I'm not sure. We will come to that later. But if, for example, this is tx, ty, tz, these are the parameters, and this will be a t in which we use minus tx, minus ty, and minus tz. Okay, so this series of multiplications to this point will have the effect of rotating this triangle around itself. Now, the implication of this in code, when you write some code in OpenGL, it's really strange in such a way that the way OpenGL works is OpenGL is not object oriented at all. It's not like you have a triangle, you say rotate triangle, do this, do that. You do not do that. It's like OpenGL is a state based. We're going to come to OpenGL soon enough in 1 week or so. So that's why I started talking about OpenGL, the forward rendering pipeline. It is like a state base. Everything is like their global states which affect the current drawing. So for example, you may have a function that says draw triangle. Okay, when you say draw triangle, the triangle is drawn on the image at this instant. The draw triangle function draws the triangle on the window, but it uses, for example, if you want to move this triangle, how are you going to do this? For example, you want to draw a triangle which is rotated. So you cannot say draw triangle and then rotate triangle. You cannot do that because this triangle is already drawn. So the way to draw a rotated triangle is at the time of the drawing of the triangle, what OpenGL does is OpenGL looks at what is the current modeling matrix, modeling transformation matrix. OpenGL maintains, it's actually called the model view matrix. You're going to see that. This model view matrix is actually a multiplication of the camera transformations with the modeling transformations. Okay, but imagine we are not going to do anything with viewing transformation. Imagine for now, because we don't know that yet. But as I said, at the time of this draw function, OpenGL looks at this global state variable, which is a 4x4 matrix, the model view matrix. Okay, it's called the model view matrix, but let's forget about this model view part. So it's nothing but this global state variable is nothing but a 4x4 matrix, and you can actually query its contents. Initially, it's just the identity matrix 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So this is the identity matrix. Initially, the model matrix, the modeling transformation matrix, you can think about it like this. So at the time of draw triangle, whatever its original coordinates are, the original coordinates that are given to this triangle, V1, what happens is that when OpenGL tries to draw this triangle, it multiplies that triangle's vertices with the current modeling matrix, modeling transformation matrix at this instant. At the execution of this line, whatever the current state modeling matrix is, it will first multiply all of your triangles vertices with that modeling matrix and then draw the triangle. So what it means is that before drawing the triangle, I need to, if you want to really rotate the triangle around its center of mass, for example, 45 degrees before drawing it, you have to have the necessary function calls to modify this modeling matrix so that it indicates this current state. So, and each of the function calls that you're going to do, for example, you're going to say translate. There are functions in OpenGL, GL translate, GL rotate. Actually, these functions have become obsolete, meaning that you have to really manage the matrix yourself. So OpenGL is getting, interestingly, each new year, OpenGL is getting lower and lower levels. It was a very high level language, high level library when it came out. But it's getting, because of the GPUs, I think, becoming their really general purpose, all the functions provided by OpenGL now, they become propagated to the users. The user has to know how to translate. So there was a GL translate function. As I said, it's obsolete, but right now there are matrix libraries. Like one of the libraries is GLM. So although OpenGL ceased to use this GL translate function now, Other third parties provided their own libraries, like this GLMS OpenGL matrix library, which contains a function similar to this GL translate. But what this GL translate does is it contains only 3 parameters. Let's call them tx, ty, tz. Okay, with this tx, ty, tz, if you call this function, what it will do is, whatever the current matrix is, it will first generate a transformation matrix with these parameters, 1, 0, 0, tx. Okay, it will generate this matrix, this call, and it will multiply it, whatever the current matrix is. This is the current matrix. It will right multiply itself. This is the translation matrix that it formed. It will right multiply itself with the current modeling matrix, and it will update the current modeling matrix. So the current model matrix is going to be assigned to this value. It updates it by right multiplying itself. Okay, now the implication of this is that consider the last call that has been, is it? Yeah, consider the last call. Okay, since it's right multiplying itself with the current matrix, what should the rightmost entry here is the first transformation that is applied to this, right? Translate this actually this txty, I mean this tx is actually whatever the center of that triangle is, that's minus that center, right? In order to move that center to origin, we need to first give the negative center coordinate values, and this minus tx is going to be plus tx. I mean, if this confused you, sorry about this. I mean, this plus this tx, ty, tz were just arbitrary random variable names. Tx, ty, tz is not the center. I mean, if this is tx, ty, tz, the center's coordinates are like minus tx, minus ty, minus tz, because the first transformation we do to move this point back to origin, it should be the negative of these coordinates to make it 0. Okay, now the implication of this order of matrix multiplications from left to right is that in your code, when you're doing the coding, you have to write your transformation you intend to apply on this in reverse order in the code. Look at this. This draw triangle is like the V1 matrix, V1 coordinate here. Whatever code you write here, GL translate, another GL translate, some GL rotate, okay, the last function call that you apply to translate this thing is this matrix, okay, because whatever the current matrix is, the last call that you make right multiplies itself with it, which means that, and this was the first transformation you apply on the point. So it's like you're writing your code in reverse order of the application of the transformations to your triangle. If you want to first translate your triangle, so this was minus tx in this example, or let me directly write the centers. If you want to move the center to origin first, this code should be closest to this draw triangle code. So this is going to be the first transformation that is applied to your triangle. This is going to be the second transformation that is applied. This is going to be the third transformation that is applied. So this may be a bit confusing, especially when you don't know the theory behind these, how these matrices are composed, how our vector is right multiplied with this current modeling transformation matrix, and the order is this way, and the closest one is the first applied transformation. If you don't know the theory behind this, OpenGL programming may be really mysterious. Why do we write the code in reverse order of the transformation? So that may be unintuitive at first, but I just wanted to give you a heads up on this. Okay, now we may continue with, so you now have an idea of how we can compose transformations by applying one of them and one after another. And in this one, if you change the order, that's one of the first bugs and newbie OpenGL programmers have, the black screen problem. They don't see anything on their screen. Then the main reason of this black screen problem is if you mix the order of the transformations, since matrix multiplication is not commutative, you are going to be moving your objects to places where you don't intend them to go. So they may go out of bounds, they may go behind the camera. So that's the bad thing about three-dimensional space, right? Three-dimensional space is much more huge than two-dimensional space. So if you not point your camera to the correct location, you're not going to see anything. You're just going to see empty space. So therefore, you need to be very careful about where your camera is looking at, where the objects are. And when you transform your objects to locations, you need to make sure the order of those transformations are correct. Because although matrix multiplication is associative, it's not commutative. Different ordering of this code will give you a different result. All right, so let me see. Oh yeah, now let's talk about scaling next. How do we scale an object? Now let's, in this new slide, let's assume I have a square, okay, with 4 units each side. So let this be a square. And I want to make it now a square. I want to halve its size. I want to make it a square of a smaller square in which each side is 2 units long. How can I do that? What kind of a transformation I'm going to apply? Look at the coordinates. Let's give these coordinates some names. For example, if this is 4, 4, 4, 4, let this be, for example, 12, maybe 8. Okay, so the coordinate here is 12, comma 8. It's this corner, and this other corner, let's call this V1, and this is V2, V3. Let's V3 is going to be 16, 12, right? So you add 4 to both of the coordinates. So 16, 12 is where this corner sits, V3, and 12, 8 is where V1 is. Now I want to halve the size. I want to just change its size so that each side is length 2. One thing to do that, for example, if we do this, x prime is like half of what x is, or sorry, and y prime is what half of original y is. So this will actually, with a scaling, so these are the scaling parameters. In 3 dimensions, we will have 3 parameters, sx, sy, and sz, which means that you can scale each dimension separately. But if you're performing uniform scaling, if you want to scale your object uniformly among all dimensions, you just need a single parameter, which is s. Okay, so it gets a parameter. This s can be larger than 1. You may want to double the size of your things. It may be 2, it may be 0.5, it may be something smaller than 0. But here, the matrix, if you want to do something like this, if you want to halve the size of your coordinates, the scaling matrix looks something like this. The scale parameters, they appear at the diagonal, 0.5, 0, 0, 0, 0, 0.5. So in 3 dimensions, the matrix is going to look like this. By the way, we don't want to scale the last dimension because we want our the last entry in our vectors, whatever x prime, y prime, z prime is, we also want this last thing to appear as 1. So this is 1 here. Okay, now let's see what will happen if I apply this transformation, the 2D version of it, which is this 3x3 matrix, in which you ignore this one, you move it here. If you consider the 2D version of this, what will happen if we halve the coordinates? V1 will be at 6, 4. Okay, 6, 4 is not here, but where's 6, 4? 6 is somewhere here, 4 is somewhere here. So this is roughly where 6, 4 is. And V3 is going to be at 8, 6. Okay, this is where like 8 is, 6 is somewhere here. So if this is 8, 6, my square is going to be, okay, it's now smaller, as you can see. It's a 2x2 square, but something happened that I didn't want. If you want your objects to become smaller, you usually want them to get smaller in place. Okay, what? Because if your goal is just to make it smaller, you don't want to also, okay, you made it smaller, but it also moved, right? Because you're just changing the coordinates by halving them like this. It became smaller, but also it moved, which was an effect I didn't want to get. For example, if you want to scale an object so that it scales and it stays in place like this, what should you do? The answer is actually, yeah, not that difficult probably. How can you scale this in place? For example, what is this? I want this 6,4 to appear like 14 something, right? Exactly, translate first origin. So we, again, the center of mass, whatever it is, the center of mass here is like 14 something, right? So yeah, 14. Yeah, we can. So this is, yeah, so we translate the center to origin. So this is, the center is 1410. So we translate first 1410 to origin. So it becomes a square with these parameters from -2 to -2 to 2, 2. Okay, so it's a really nice looking square with centered around origin. If you double the size now, what will happen is these -2s are going to be -1. So it will be a nice, if you apply this transformation, the scaling, to something that is centered around origin, as you can see, it didn't move at all. Its center still stayed at the center, -1, -1, and this is 1, 1. After it became -1, -1, 1, 1, you translate it back to this original location. Okay, so this -1, you add 14 to that. But am I doing something wrong? This -1. Oh, actually, we are moving this to 4. Yeah, so we subtracted 14 from this. It became -2, and we need to add back 14 to this. So its coordinates will be 13. Yeah, actually, it's centered, so it's correct. So if it will be like 13. If you add 10 to this, 13. No. So this is 10. Yeah, if you add 10 to the 13, 9. So 13, from 13, 9 to 15, 11. And it's exactly, it's like, it moved 1 unit in each direction. So it became, its size is half. Okay, from 13, 9 to 15, 11. This is what it will be if you add 14, 10 to this. And if you add 14, 10, this will be 15, 11. Okay, so this is, if you, the same thing. First translate whatever the pivot point you want to scale around. So it's like the scale around the pivot point. You first translate that pivot to origin, then do the scaling and translate back. Okay, these are to origin, translate to origin, and then back. And the order of translations is this is your vertex. This is the first thing that is applied. Then you apply this, then you apply that. Okay. So if you understand this, you will be very comfortable in solving questions that are like these. There's another transformation, which is reflection. We may want to reflect things around certain axes. Reflection is like this. For example, if you want to reflect, if this is some object, and if you want to reflect it with respect to x-axis, which means that it's reflection. If there was a mirror, imagine there was a mirror at the x-axis. This is v1, this is v3. The reflection is going to do will appear something like this. This is v1 and this is v3. Okay, as you can see, its reflection is not just translation. Okay, although it's a square and the effect seems to be like this. v1 is here, v3 is here. And reflection is nothing but, as you can see, the y coordinates did not change. So the y coordinate, exactly. So actually the y coordinates change. The x coordinates do not change. Thank you for us. So the correct thing is to have a scale factor of -1. If you scale if your scale parameter is -1, it will have an effect of reflecting with respect to the x-axis. So this is if you change your y-coordinate, you're reflecting with respect to x-axis. If you change your x-coordinate, on the other hand, it's reflection with respect to the y-coordinate. Now, here is a question. I think this was one of the questions in some earlier midterms or so. We are given a mirror in our scene. Okay, this is a mirror. Some mirror given to us with 2 endpoints on it. Okay, I have a mirror, and this is its back. Its front is this way, and I have a triangle here, and I want to generate its mirror reflection, the mirror reflection of this triangle, however it's going to look like. I want to generate it over this side. Give me the transformation matrix, let's call it M. Find M that will translate this triangle. So these 2 points are also given to us. Okay, find M to translate this mirror, translate this triangle with respect to this mirror. What are you going to do? How are you going to solve this problem? The idea again is the same. Make this mirror either the y-axis or the x-axis. So we need to have a necessary transform, because it's difficult. So what are you reflecting? If you say -1 to x coordinate, it's not -1. If you look at the mirror reflection of this triangle around this mirror, it's something like it looks even like rotated. All right. So what you need to do is move the mirror to either align the mirror with the x-axis or the y-axis, and then perform the reflection, then multiply it with -1. So if you, for example, align, how do you align this mirror with the x-axis? Move point P2 here. Okay, if you move point P2 here, it will be something like this. Or you can move P1, it doesn't matter. So there are alternative solutions to this. If you move P2 to origin, it will be like this. And then you rotate the mirror alpha degrees, so that this one is the x-axis. Okay, so this alpha degrees, what is the angle? You can actually find it with respect to the coordinates, but we will see a better algorithm, an alternative method to align arbitrary vectors with the major axes. We can actually, we'll see a method that we can define our own basis vectors. If this P2 to P1 becomes the x-axis, there will be a new y-axis when P2, P1 is x-axis. This is called forming a basis, coordinate reference basis. And this alternative technique, you will not need to find what alpha is. Okay, actually we don't really need to know the alpha itself, right? Can we move one of the axes to the mirror? If you move the axis to the mirror, what will be the effect? So if you moving the axis, a good question. If you move the axis to the mirror, its effect is it will be like the mirror is going to be like here. For example, if you try to move the x-axis onto the mirror, what it will be doing is that the x-axis becomes here. While you're doing that, what happens is that all the objects move along with it. You're not just moving, you cannot move individual objects. That's when you're making these transformations, they're global. You change your worldview. All right, so you apply it on every one of those. So moving the one of the axes to the mirror, it will have the effect of, if this becomes x-axis, okay, and this is y, like this, your mirror is going to appear. If you just I try to do a relative movement of this, it's going to be something like this. Okay, P2, P1. Okay, it will be some arbitrary orientation, and the triangle is also moved here. As you can see in this new coordinate system, again, it's not -1 or 1. We cannot. It doesn't become a major axis. So moving the mirror to this one, it's like. Actually, it doesn't provide us anything. You can try it yourself. And the best thing to actually to make some of these things to digest the material, you can try it on simple examples. Okay, for example, you can give real coordinate values, have a mirror which is like 45-degree angle here, some simple values, give its coordinates, and try to perform a translation in which the x-axis is moved to the mirror. What you should do to move the x-axis, for example, perform the translation in reverse order and see whether it's going to work or not, whether you'll be able to find the correct mirror reflection of that object. I'm going to show an example of this when we come to camera transformation. Camera transformation is a little bit tricky. It's unintuitive because in order to move from a new old coordinate system to a new coordinate system, what we will do is something really unintuitive. We will do something reverse. We will make the transformations that are necessary to align the new one onto the old one. It's like we're changing, and this will be the correct transformation for the camera. And for that, I'm going to give you an example in which you'll see it makes sense to do what we're doing. The computation is going to be correct that way. But for now, for this mirror reflection, coming up with a simple example in this in 5 minutes may not be simple. You need some pen and paper to work on it to see why it works like this. But the main idea is this. If you're rotating around arbitrary something, if you want to reflect around something arbitrary, what the first transformation you do is you make this arbitrary thing something standard. Let's get rid of the arbitrariness of this mirror. It will be really nice if the mirror was the x-axis itself, right? I mean, if I tell you, if the same question is like this, okay, instead of this arbitrary mirror, if we ask the question in such a way that this is the mirror, okay, this is your triangle, find the reflection, write the transformation matrix to reflect this triangle with respect to this mirror. So it will be really easy, right? 1, 0, 0, and 0, -1, 0. You will immediately write this, okay, because you only need to do the y-axis change. So this is the easy case. So in order to get to this easy case, what happened? As you can see, in order to get to this easy case, the mirror has to be here. Okay, so therefore we transform the mirror to this location. When we do the transformation, but we cannot leave it like this. We need to get back to its original position, and this is why we do that. But these are good questions. I mean, thinking about whether it's possible to do the different ordering, and you can. Some of them are not very intuitive. But you may try, as I said, some numerical examples to see which one is going to work or not. And when you're working on it on paper, you'll probably understand why we do it like this. If you really work on real numbers to try to solve this problem. Okay, so that's we have seen scaling, reflection, translation. This translation, rotation, and scaling, these three are the basic transformations. Okay, with this, reflection is just a specific case of scaling in which we allow negative numbers. Uniform scaling is in which all the coordinate axes are scaled uniformly with the same scaling value. Then one question: shouldn't we bring triangle with mirror? With mirror and rotate with it? Exactly. What happens is when we perform this, when I move the mirror here, when I make the necessary, everything in the world moves with it. So the triangle. So when you write the transformation to make the mirror move to the x-axis, that transformation you apply actually on the triangle itself. So it's not only just moving the mirror, you're moving all of your objects along with it. So the triangle also moves and rotates. So actually, in order to perform the first thing before the reflection, you need two transformations: one translation, then rotation. Okay, then let's call this rotation, translation, and then reflection. Okay, so 3 of them. Then we need to do undo the rotation, and undo translation. So you can perform this in 5 steps. In order to find the composite transformation matrix, you need to multiply 5 3 by 3 matrices with it. Yeah, when we use the reflection matrix, we reflect all of the objects, not the triangle. Now, so how can we apply different transformations to different objects then? That's an interesting question. I want to reflect a triangle here, but if there's an object here, for example, there's a circle here, I don't want to reflect it. I just want to view it like this. The way we do that is, before we draw objects, we apply different transformation matrices on them. For example, whatever reflection matrix you have computed here, let's call it M reflection. Before drawing the triangle, we say, okay, this is M reflection, draw the triangle now. But before we draw the sphere, we shouldn't multiply it with this reflection matrix. So we need to get to the previous version of the matrix in which it wasn't reflected. We need to probably, so there are multiple, for example, it may be the case that these two may be moving together along on the x-axis together. So which means that there's some translation first you applied. For example, what if they happen to be this circle and this triangle happens to be on a wagon in a train, all right? And the train is moving at a constant speed, and you're providing this animation, which means that you're moving both of them. So both of them translate in some plus positive x direction at every frame. So you're changing some modeling matrix which happens to applies to both of them. Let's call it the movement of the train, M train. This matrix that moves both of them is M train. Then what you can do is this. Either you may be careful and call M before, so you apply M train, draw circle, and then apply the reflection, M train multiplied by reflection. Okay, so you can, if you just do reflection, it will you will probably not be applying the movement of the train too. So the movement of the train, in addition to that, you reflect with respect to the mirror, then draw the triangle. Okay, so while you're drawing your objects, you make sure the correct modeling transformations are applied on them by changing the modeling transformation just before you draw them. So what happens, I mean, if ordering the objects, in which order should we draw them so that certain modeling transformations are not applied on them? This may be very difficult to maintain if you have lots of objects in your system, right? The good thing is that there's a mechanism based on stacks in OpenGL. You can actually maintain a number of matrices. For example, you can say that, for example, if you just want to apply a transformation only applying on an object, what you can do is you can save the current version of the matrix, because after we multiply it with mref, the current version of the matrix is gone. But what if there is a function that helps us to save the last version of the matrix on a stack of matrices? That's called the push matrix. There's a function called push matrix. Its main purpose is it copies the current transformation matrix and puts it on a stack. So then, so there are two copies on it, and then you apply transformations, for example, reflections, and then always the top of the matrix is used. Whatever we have on the top of the matrix, that's the current matrix. That is used to on the objects that are drawn. So when we draw the triangle, we apply this reference reflection and then draw it. And what if there's an object here in which we don't want to reflect? What do? We say pop matrix, which will get rid of the top of the matrix. Now the new top of the matrix is going to be this one, which was the matrix that was saved earlier. So this push matrix is like save the current state. Then you can apply whatever on it, draw your new object, and as soon as you pop the matrix, you get back to your previous state. So you maintain the states of matrices with this push matrix, pop matrix. Yeah, if you want only a triangle to be reflected, so I think this answers Bura's question too. If you want only a triangle to be reflected, so what we do is we push the matrix, we apply the reflection on that copy matrix that is now on the top. We draw the triangle, and then we pop matrix, and then we are back in the non-reflected world. All right, so this is how it's a way to save your state of matrices. You can also have your own individual, you can have a different way to maintain your own matrices. As I said, it was like this in the previous versions of OpenGL. These functions were very useful. You were just calling it to maintain. These days, you have your own OpenGL library became very low level. You have to maintain your own matrices and variables. And actually you do the multiplication before you send you call the draw command. Okay, there is no global state anymore. So and in programmable shaders, you send those matrices to your to the GPU as well with some variable uniform variables, and in the GPU you multiply your vertices. You do the multiplication yourself. If you write a vertex shader, this process of this vertex coordinate multiplied by the modeling view matrix, you do this yourself. You write the code to do this on a vertex shader. So everything became whatever OpenGL was doing automatically in the background is something now the users have to do themselves if they write programmable shaders. Okay, so we will talk more about this when we come to some example OpenGL programs. But just know that the main idea you should get from this discussion is that there is so like OpenGL is like a state-based thing. It's not object-oriented. That there are no triangle objects. You just issue draw triangle commands, draw circle commands, and whatever the current state is, for example, whatever the current pan color is, before you draw that triangle, it will be drawn in that pan color. You cannot say the triangle is red. You just need to, the current pan color is this. Draw these vertices, whatever the current pan color is, it will be drawn in that color. So they're just these global states. It makes it actually very error prone because what if you have a function, you work on something and you change some state variable and you forget to get it back into its previous state? So these global states make it very easy to have side effects. These different functions may be changing a global variable that you think that is not changed, and then at the end you may get bugs in your programs. So you have to be very careful about what you're doing, what the states are. So there are nice programming conventions in OpenGL. For example, if you do something, if you change something before you exit the function, you get back you change it back to its original state, for example, so that whoever called you reduce these side effects. All right, so let's see what we have on the slides, and then we're going to have a break. I think we have covered all the modeling transformations. We have talked about scaling. I've talked about this homogeneous coordinates where we have the additional coordinate, and the way the homogeneous coordinate works actually is that it has also a meaning. If it's something other than 1, the actual coordinates are found out by dividing the coordinates by the last entry. So if I have a 2-dimensional point and this third dimension is some h in the homogeneous coordinate, its 2-dimensional coordinate is actually xh divided by h. So this last coordinate is like a dividing factor. And since we were just always using 1 in our case, if you have xy1, it means that the 2D coordinate is actually xy, okay, if it's 1. But we'll see that this last entry will help us to make transformations which are non-linear. For example, if this is a variable, so this will be something really interesting, right? For example, let me write it here. In this current linear version, we cannot do something like this. In this current linear version, can you do something like this? X is equal to, or x over z. X prime is equal to x over z. Y prime is equal to y over z. Look at this. Is it possible in a linear transformation? No. I mean, our form is like this: ax plus bx, sorry, by plus cz plus d. Look at this. Is it possible to divide your x coordinate by z and to find x prime? No, it's not possible. But when do you think we are going to need an equation like this? Why do we want to divide x coordinate by z coordinates? Any ideas? Any any answers to this? This we will require something like this. When do you want to divide a coordinate by z? What is z here? I mean, why does the z coordinate need to be? Yeah, why does the x coordinate divided by z? Any answers to this? I will wait. Yeah, it's to transform 3D to 2D. That's an answer. That may be an answer. It may be considered correct. I mean, I could just transform 3D to 2D with this too, right? For example, if I have x, y, z, I can just say the new in the 2D, x is equal to x. We'll also transform it. Y is equal to y, and z is equal to some constant value. For example, if I do this, x is equal to x, y is equal to y, z is equal to 5. Okay, any points that are here, I will just be using its first two dimensions. That's also 3D to 2D. Yeah, to bend the objects, what kind of a bend is this? Actually, it's something very common in everyday life. You did this in ray tracing without even knowing it. The keyword here is perspective. Okay, so what happens? For example, if this z, if the z coordinate of an object is large, which means that, I mean, if the camera was at 0, 0, actually I can divide it by, I can take it minus of this to make it more correct, minus z. So z will be like the distance of the object to the camera, which means that farther objects will be made more smaller. This is what perspective is, right? I mean, far away objects appear smaller. You scale them more. Nearby objects appear larger. This is how we will be able to performing perspective. This is sometimes called perspective divide. And since we will not be able to do it with matrix multiplication, what we will be doing is that this last coordinate, x, y, z, w, this w here will not be 1 anymore. It will be some value computed with respect to z. All right, so the last row here in your matrix will be something like 0, 0, 1, 0. If it was 0, 0, or if it's 0, 0, minus 1, 0, what happens? You see, the last coordinate becomes this here. Your point will be something like x, y, z, and z. Okay, if it's something like x, y, z, and z, which means that in 3 dimensions, this coordinate, it's x coordinate. This will be, so this is like a 4-dimensional point, but its 3-dimensional version, it will be like x divided by z, y divided by z, z divided by z. Okay, so this is the 3-dimensional point. So this last coordinate allowed us to perform, I mean, in 4 dimensions, it's still a linear transformation. The x coordinate does not have anything divided by some variable. This is like this. But if we have some number other than 1 in the 4th dimension, when we are converting this 4-dimensional point and when we are treating it as 3-dimensional point, we said that in that slide we are dividing by this h, and if that's h, if you put z there, you will, in 3 dimensions, you will be making this division of your coordinates by some variable, and this variable will be the distance of those objects to the camera. Okay, but in reality, if the camera is anywhere, if it's looking in any direction, it's not the z coordinate that's the distance, right? We need to compute the actual distance. But that will bring us to our next topic. That will be very difficult to do. I mean, to do the perspective, if the camera is in just arbitrary location, looking at arbitrary direction, its distance may be the y coordinate if it's looking up. If it's looking along the x-axis, the camera is looking along the x-axis, the x-coordinate will be its distance from the camera. So we cannot always divide by z. So what we will be doing is, in order to perform this perspective operations easier, we are going to say this. Okay, even if the camera is in an arbitrary location and an arbitrary looking in an arbitrary direction, why don't we change our world so that camera is the origin and it's looking at minus z direction? That's the purpose of weaving transformations that we will see next. Okay. Homogeneous coordinates could be considered also as intuitively as a plane projections on points on planes. But the main purpose, as I said, is to have a dividing factor. And we also see the first purpose was to have translation as matrix multiplication. By using this 1 as the last coordinate, it helps us to do that. The second purpose is to have this division perspective divide is possible with the help of the fourth coordinate, because otherwise it's not a linear transformation. And this is a summary of the matrices in 2D we called. Oh, okay, so this transforming vectors, I'm going to talk about it after the break. So that's something we need to discuss actually. When we are transforming objects, rotate, scale them. What about vectors? If we rotate, scale, translate vectors, what happens to them? So we are going to talk about that after the break, because we will be, while we are moving the objects, we may also want to do something to their normal vectors. In 3 dimensions, we may have triangles and they may have normal vectors. So how do we update the normal vectors of the triangles? Do we treat them as points? Because vectors are also like in 3 dimensions, they're like 3-dimensional points. If they apply the same thing on a vector, what happens? So how do we transform these normals? Let's talk about them after a 10-minute break. All right, so I will stop sharing now, and I will be back at 10:47. All right, see you in 10 minutes.